Welcome back to the deep dive. We're the show where we try to distill complex stuff into, well, surprising facts and insights you can actually use.
Yeah.
And if you've ever seen those Hollywood movies where a chemist just, whips up some incredibly complex molecule overnight.
Oh, yeah. Totally unrealistic.
Right. The reality in organic synthesis, it's traditionally taken years, sometimes even decades. I mean, each step is just painstaking.
It really is. You've got the planning, setting up the glassware, running the reaction itself, then isolating, purifying, confirming the structure.
Assuming it even worked.
Exactly.
Yep.
Assuming it worked perfectly.
But that's where it gets really interesting, and it's kind of our mission for today's deep dive. The whole field of organic chemistry, it's constantly changing. Breakthroughs are letting chemists build these incredibly complex structures way faster than before. So we're going to explore some of these really groundbreaking transformations. They've fundamentally changed the whole art of making molecules.
Yeah, that's right. Our focus today is squarely on a special class of compounds, organometallic compounds. And the unique reactivity they bring to the table will really dig into the revolutionary reactions they enable, especially when you pair them up with transition metal catalysts. Think of it like a journey,
Yeah.
through the key ideas and how they're actually used in practice. It's transformed the field.
Okay, let's start with the basics then. What exactly is an organometallic compound?
Simply put, it's any compound where you have a direct chemical bond between a carbon atom and a metal atom, a CM bond.
Right, and we've actually run into some of these before, haven't we? Like organolithium compounds, RLI, and those super versatile Grignard reagents, the organomagnesium ones, RMGX.
Yep, those are classic. And organocopper compounds, too, like R2-Sulai, the Gilman reagents.
Okay, so what's the big deal? Why are they so useful?
Well, the fundamental thing is how that carbon atom behaves in the carbon-metal bond. It's often counterintuitive. Carbon is usually more electronegative than the metal it's bonded to.
Meaning it pulls electrons towards itself?
Exactly. So the carbon atom becomes electron-rich. It gets this partial negative charge. It essentially acts like a carbanion, a carbon-based anion.
Ah, okay. So unlike, say, methyl chloride, where the chlorine pulls electrons away from carbon,
Right, making that carbon electron poor and electrophile.
in something like methyllithium, the carbon pulls electrons from the lithium.
Precisely. Making that carbon electron-rich nucleophilic. It becomes a source of carbon that wants to attack electron-deficient centers.
Huh.
That's the key. And, the specific metal matters a lot. It really affects how electron-rich that carbon is, and therefore how reactive the whole compound is. For instance, the electronegativity difference between carbon and magnesium is, well, it's much bigger than between carbon and copper.
Okay.
So organomagnesium compounds the Grignards. They are much stronger nucleophiles and also much stronger bases than the organocopper reagents.
And that explains why they react differently sometimes. We've seen that, right? Like Grignards hitting acid halides twice to make alcohol.
Yep, brute force.
While the organocopper reagents, the Gilmans, they stop nicely at the ketone stage. Just one reaction.
Exactly, more selective. And remember the Michael addition, the 134 addition.
Well, yeah, organocoppers are great for that. Adding to the double bond of an unsaturated ketone. Grignards tend to just hit the carbonyl carbon, the 12-2 addition.
Right. That selectivity is crucial for building complex molecules step by step. So, building on that, the CLI and CMG bonds, they're highly ionic in character. This makes RLI and RMGX compounds act as incredibly strong bases and nucleophiles.
Like among the strongest available?
Pretty much, yeah. Some of the strongest tools chemists have for forming new carbon bonds with electrophiles. It's their superpower.
And speaking of superpowers, wasn't there a Nobel Prize for this? Grignard reagents?
There was. Victor Grignard won it back in 1912 for his work on these organomagnesium compounds, a real foundational discovery.
That's amazing. So how do you actually make these things?
Well, for organolithium's RLI, you typically take an organohalide that's just an organic molecule with a halogen, like bromine or chlorine, and react it with lithium metal, usually in a nonpolar solvent like hexane. For Grignard's, RMGX, you take your organohalide and react it with magnesium metal, but this time in an ether solvent, something like diethyl ether or maybe THF.
Why the ether?
Good question. The ether solvent is critical because it coordinates to the magnesium. It stabilizes the Grignard region as it forms. Without it, it often doesn't work well.
Okay. And does it matter which halogen you use?
Reactivity generally goes iodides, bromides, chlorides, so iodides react fastest, but bromides are often used because they're a good balance of reactivity and cost and maybe stability. But, and this is a big but, their immense reactivity has a downside, an Achilles heel, you could say.
Because they're such strong bases.
Exactly. They react instantly and irreversibly with water. Just rips a proton off water to form a simple hydrocarbon, RH.
Which is why you need strictly anhydrous dry conditions.
Absolutely critical. And it's not just water. They'll react with any functional group that has even a weakly acidic proton. Think alcohols, OH, amines, NH, thiols, SH, terminal alkynes, that's CCH proton, carboxylic acids.
So if you have those groups in your starting material,
Your organolithium or Grignard reagent will just deprotonate that group instead of doing the reaction you want it to do.
yeah,
It's a really common mistake for students, forgetting to account for those acidic protons.
right, got to protect those groups or choose a different starting material. But when you do handle them right, they're incredibly versatile nucleophiles. We've seen them react with ketones and aldehydes to make alcohols, epoxides also to make alcohols, CO2 to make carboxylic acids.
Yep.
Esters react twice to give tertiary alcohols, nitriles to give ketones after hydrolysis.
Exactly. They're workhorses for CC bond formation.
Okay, but what if you need something a bit gentler, more selective?
That's where the Gilman reagents come in. Lithium dialkyl cuprates, R2-Sule, named after Henry Gilman. They offer much more controlled, selective carbon nucleophilic reactions.
How do you make those?
It's usually a two-step thing. First, you make an organolithium, RLI, just like we discussed. Then you react that with a copper I halide, like copper I iodide, QI. And the R group here can be alkyl, aryl, or vinyl. Pretty flexible.
And their selectivity is the key point, right? We
Yeah.
mentioned the acid halide to ketone reaction.
Right. They stop cleanly the ketone, unlike Grignards. And they are fantastic for that 1 bill of 4 Michael addition to II unsaturated ketones, where Grignards prefer the 1 bill of 2 addition. Huge difference in where the new bond forms.
And this leads to a specific named reaction, doesn't it? The Corey-Posner-Whitesides-House reaction.
Yes, exactly. That's a coupling reaction where a Gilman reagent, R2-thioli, reacts with another organohalide, RX, to form a new RR carbon-carbon bond.
Okay, coupling two different pieces together.
Precisely. You usually run it in ether solvents, often at low temperatures because the Gilman reagents aren't super stable when warm.
What kind of organohalide RX works here?
It works well with methyl halides, primary alkyl halides, vinyl halides, and aryl halides. Doesn't usually work well with tertiary halides or even most secondary ones because elimination side reactions tend to take over, though some cyclic secondary halides are okay.
And the R group from the Gilman reagent.
That can be alkyl, aryl, or vinyl, so you can connect quite a variety of pieces. And interestingly, usually only one of the two R groups on the copper actually transfers. The other one's sort of sacrificial. And another really crucial feature, stereospecificity. Meaning if you have a double bond, say a CC bond, in either the Gilman reagent or the organohalide you're coupling it with, its configuration, whether it's cis, Z, or trans E, is perfectly preserved in the final product.
Wow, that's incredibly precise control.
It is. Invaluable for making complex molecules where the 3D shape is critical.
So practically speaking, this reaction is powerful because it lets you join different carbon bits together and it doesn't mess up other functional groups like ketones or esters.
Exactly. High functional group tolerance. That's a huge deal.
Yeah.
That means you don't need complex protecting group strategies, saving potentially many steps in a synthesis. It was a really important reaction, kind of setting the stage for even more versatile coupling methods we'll get to.
Okay, cool. Let's switch metals again. What about zinc? Organozinc compounds.
Right, CZM bonds. You can make them similarly to Grignards, but the bond itself is generally considered more polar covalent, less purely ionic than CMG or CLi.
And is there a standout reaction here?
Definitely. The Simmons-Smith reaction, using a specific organozinc reagent, isomethyl zinc iodide, or ICH2ZNI, developed by Howard Simmons and Ronald Smith back in the late 50s.
How's that made?
You treat diadomethane, CH2I2, with a zinc-copper couple. It's like activated zinc metal.
And what does it do?
Its main thing is cyclopropanation. It reacts with alpenes, double bonds, to form a 3-membered ring. It effectively adds a CH2 group, a methylene group, across that double bond.
So you turn an alkene into a cyclopropane.
Exactly. And it does this very cleanly. And importantly, just like the Gilman coupling, it's stereospecific. If you start with a cis-alkene, you get a cis-disubstituted cyclopropane. Start with trans, you get trans. The alkene geometry is perfectly preserved.
Now, you said it adds a CH2 group. That sounds a bit like carbenes. Aren't those like C with just 2 bonds and 2 electrons?
Good connection. Yes. Carbenes are these highly reactive intermediates, often electrophilic. Dichlorocarbene is a common example.
So is Simmons-Smith using a carbene?
Well, its action looks like what a free methylene carbene CH2 might do, which is why ICH2ZNI is called a carbanoid reagent. It behaves like a carbene. But the key difference is the actual mechanism. The Simmons-Smith reaction is thought to be concerted. It happens all in one step, transferring the CH2 group directly from the zinc complex to the alkene. There's no free, highly reactive carbene intermediate floating around.
Ah, okay. And that's better
Because free carbenes are often so reactive, they can lead to side reactions and unwanted byproducts. The concerted carbanoid mechanism is much cleaner and more controlled for making cyclopropanes.
makes sense. All right, so we've seen lithium, magnesium, copper, zinc. This is already quite a toolbox, but I get the feeling we're about to hit another level.
You could say that. We're moving into the era of transition metal catalysis, particularly palladium Pi. This area has just fundamentally revolutionized synthetic organic chemistry in the last few decades.
Transition metals, they form complexes with ligands, right? And there's that 18-electron rule, kind of like the octet rule, but for transition metals.
Exactly. The 18-electron rule is a guideline for stability in many transition metal complexes. Metals often strive to get 18 valence electrons through bonding and back bonding with ligands. But the really reactive species, the ones that do the catalytic work, are often complexes with fewer than 18 electrons. They're called coordinatively unsaturated. They have open coordination sites ready to interact with reactants.
Okay, so these unsaturated palladium complexes are key. And the first big reaction here is...
Let's talk about the Still coupling, pioneered by John Still. It's become an incredibly powerful and widely used method for making carbon-carbon bonds.
What does it couple?
It couples organostanins, that's compounds with a carbon-tin bond, CSN with organic electrophiles, usually organohalides or triflates, and it's catalyzed by palladium.
Organostanins. Tin compounds. Okay. What kind of groups can you join?
The real power here is joining sp2 carbons. So the R group from the stan-N and the R group from the electrophile can typically be aryl groups like benzene rings or vinyl groups, parts of double bonds. The leaving group X on the electrophile is usually a halide like iodide or bromide or a triflate.
So you could link two aromatic rings together, a biaryl.
Yep, or an aryl group and a vinyl group to make a styrene derivative, or even two vinyl groups to make a conjugated diene. Really versatile for building complex frameworks.
And does it preserve double bond geometry?
Yes, it's stereospecific. The EZ configuration of any double bonds involved is retained, which is, again, super important. And these organostanins, they're actually quite nice to work with in many cases. A lot are commercially available or relatively easy to make. And importantly, they tend to be stable to oxygen and moisture.
Oh, that's a big practical plus compared to Grignards or organolithiums.
Huge plus. But their real superpower is their functional group tolerance. They can react selectively even if there are other groups like ketones, esters, amides, nitriles present in the molecule.
So less need for protecting groups again.
Exactly. It dramatically simplifies synthetic planning.
Okay, how does the palladium make this happen? The catalytic cycle.
Right. The proposed cycle usually involves three key steps running over and over. First is oxidative addition. The organic electrophile, Rx, reacts with the palladium catalyst, inserting the palladium into the Rx bond to form a palladium species.
Okay, palladium gets involved.
Then comes transmetallation. The R group from the organostanin, Rs and B pre, for example, transfers from the tin atom to the palladium atom, displacing the leaving group X. Now both R and R are attached to palladium.
Tin gives its R group to palladium.
Yep. And finally, reductive elimination. The R and R groups on palladium couple together, forming the new RR bond, and they leave the palladium. This regenerates the original palladium catalyst, which can then start another cycle.
Oxidative addition, transmetallation, reductive elimination. Got it. Like a little molecular machine.
Precisely.
Okay, so that's still using tin. What about Suzuki coupling? That also won a Nobel Prize, right?
Yes, Akira Suzuki shared the 2010 Nobel with Heck and Negishi. Suzuki coupling is conceptually very similar to Still, but instead of organotin compounds, it uses organoboron compounds.
Boron instead of tin. Any other key differences?
The big one is that Suzuki coupling requires a base to work, in addition to the palladium catalyst. Still generally doesn't need added base.
Okay, base is essential. What kind of boron compounds?
Things like organoboranes, boronic acids, RBOH2, or boronic esters. And the R group can be vinyl, aryl, allyl. But critically, it can also be alkyl.
Ah, so Suzuki can make sp3-sp2 bonds using alkyl groups. Still was mostly sp2-sp2, right?
Mostly, yes. That ability to readily incorporate alkyl groups is a major advantage of Suzuki coupling, significantly broadening its scope.
What other advantages does Suzuki have?
Well, the boron byproducts are generally considered less toxic and easier to remove than the tin byproducts from still. Organoboron reagents are often cheaper too, so it's often seen as a greener alternative.
And then besides.
The main one relates to that required base. If your starting materials have acidic protons near carbonyl groups, the base can sometimes cause unwanted side reactions, like aldol condensations. So you have to be mindful of that.
How are the organoboron compounds made?
Often by hydroboration of alkanes, or alkynes, which we've seen before. Or you can make aryl boronic acids from arylithium compounds. They're quite accessible.
And the mechanism, similar to still, but with the base doing something.
Largely parallel, yes. Oxidative addition, transmetallation, reductive elimination.
Right.
But the base plays a crucial role. It's thought to interact with both the palladium intermediate and the organoboron compound. It helps activate the boron compound, making it easier to transfer its R group to palladium in the transmetallation step, which is often rate limiting.
Clever. So the base isn't just mopping up acid, it's actively helping the reaction go.
Seems to be the case, yeah.
All right. Still tin. Suzuki. Boron. There's one more from that 2010 Nobel trio, Negishi coupling.
Right, Eiichi Negishi. His coupling reaction typically uses organometallic species containing zinc, although aluminum or zirconium can sometimes be used too. The catalyst is often palladium again, or sometimes nickel. We'll focus on the organozinc version.
Zinc again, like Simmons-Smith, but for coupling. Are these organozinc reagents different from the boron or tin ones?
Yes, generally they're more reactive. Zinc is less electronegative than tin or boron, so the carbon-zinc bond is more polar, more carbanionic in character.
More reactive, so it works when the others don't.
It can, yes. Negishi coupling can sometimes succeed where Still or Suzuki might be sluggish or fail. The downside is that this higher reactivity often means the organozinc reagents are more sensitive to air and moisture.
So maybe you need stricter inert atmosphere techniques.
Traditionally, yes, although newer formulations using zinc salts can make them more user-friendly.
What kind of groups can Negishi couple?
It's incredibly broad. The R group on the zinc can be vinyl, aryl, alkanol, benzyl, or alkyl, and the organic electrophile partner can be allyl, benzyl, vinyl, aryl, or even alkyl halides under the right conditions. It can even form sp3-sp3 bonds, which is quite challenging otherwise.
Wow, sp3-sp3 coupling. That's powerful. How do you make the organozinc reagents?
Two main ways. Either you take a preformed carbanion, like an organolithium or a Grignard reagent, and react it with a zinc halide, ZnX2, or you could do a direct insertion of zinc metal into an organohalide, similar to making a Grignard.
Okay, and the mechanism? Still the same palladium cycle?
Pretty much analogous to Still and Suzuki. Oxidative addition, transmetallation, this time from zinc to palladium, and reductive elimination. That core catalytic cycle is remarkably robust. And just to give you a sense of its power in practice, Negishi coupling was a key step in constructing complex natural products like beta-carotene, the molecule that makes carrots orange. Specific CC bonds were formed using this chemistry. It really shows its utility.
That's a great example. Okay, 3 amazing palladium-catalyzed cross-coupling reactions. Still, Suzuki, Negishi. But there's another big one, also palladium-catalyzed, also part of that Nobel Prize, the Heck reaction.
Yes, Richard Heck. The Heck reaction is a bit different in concept. It couples an aryl, vinyl, or benzyl halide directly with an alkene.
With an alkene, not another organometallic piece.
Exactly. And what it does is replace one of the hydrogen atoms on the alkene's double bond, the vinylic hydrogen, with the R group from the halide.
Okay, so you're functionalizing an alkene directly. That sounds useful.
It is. The conditions are again typically a palladium catalyst and a base. Iodides work best as the halide, but bromides and triflates are very common too. The new CC bond formed is always between two CP2 hybridized carbons.
What's the big advantage here?
The main advantage is you don't need to preform an organometallic reagent like an organostannin or organoborane. You just take your halide and your alkene, add catalyst and base, and go. It potentially saves steps. There's also important selectivity to consider. Regioselectivity. The R group usually adds to the less substituted carbon of the alkene double bond.
The one with more hydrogens attached.
Generally, yes. And it's often highly stereoselective, frequently giving the trans or IE isomer of the product alkene preferentially, sometimes exclusively. If you use a vinyl halide, it's also stereospecific. The double bond geometry of the vinyl halide is retained.
Fascinating. What's the mechanism look like for this one? It must be different if there's no transmetallation from another metal.
It is different. It still starts with oxidative addition of the organohalide, RX, to palladium 0, but then instead of transmetallation, the RPDX intermediate undergoes syn addition across the alkene's pi bond. Both the R group and the palladium add to the same face of the double bond.
Okay, R and PD are now attached to adjacent carbons of the original alkene.
Right. Then there's usually a conformational change, rotation around the CC bond, to get the palladium and a hydrogen atom on the adjacent carbon into the right position for the next step.
Which is?
Syn-reductive elimination of palladium and that hydrogen atom as HPDX. This elimination also happens from the same face, forming the new CC double bond of the product and releasing the R group attached to the alkene.
So the PAD takes a hydrogen with it when it leaves.
Essentially, yes.
Yeah.
And finally, the base comes in to react with the HPDX species, regenerating the active PD-NEGO catalyst so the cycle can continue.
Wow. A different but equally elegant cycle. Oxidative addition, syn addition to alkene, rotation, syn elimination of PDH.
That's the generally accepted picture. And like the other palladium couplings, the Heck reaction tolerates a wide range of functional groups: alcohols, ethers, aldehydes, ketones, esters, making it incredibly valuable.
Okay, this palladium chemistry is just mind-blowing in its versatility. Are we done with the revolutions?
Not quite. There's one more major area, another Nobel Prize winner, this one from 2005, that we absolutely have to cover: alkene metathesis.
Alkene metathesis. The name sounds like changing partners.
Exactly. Metathesis means change position or transpose. In this context, it refers to reactions that basically cut carbon double bonds and then recombine the fragments in new ways. It's like reshuffling the ends of alkenes. The prize went to Yves Chauvin, Robert Grubbs, and Richard Schrock for figuring out the mechanism and developing powerful catalysts.
Okay, reshuffling double bonds. How does that work? What makes it happen?
It relies on very special catalysts, metal alkylidines. These are complexes containing a direct metal-carbon double bond, MCR2.
A metal-carbon double bond. That's unusual.
It is. The two main families are Schrock catalysts, based on molybdenum or tungsten, which are incredibly reactive, but often sensitive to air and moisture. And then there are the Grubbs catalysts, based on ruthenium.
Grubbs. I've heard that name a lot.
You probably have. Grubbs catalysts are generally much more stable to air and moisture, easier to handle, and have become the workhorses for routine metathesis in many labs.
So what happens in a typical metathesis reaction?
Well, imagine you have an alkene. The catalyst effectively breaks the CEC double bond and then reforms it, potentially swapping partners with another alkene molecule or even another part of the same molecule. If you start with simple terminal alkenes, like RCHCH2, you often get a mixture of the E and Z isomers of the new internal alkene, RCHCHR, but critically you also produce ethylene gas, CH2CH2.
Ethylene gas. Does that matter?
It matters hugely. Because ethylene is a gas, it bubbles out of the reaction mixture. Le Chatelier's principle tells us that removing a product drives the equilibrium forward. So the formation and escape of ethylene drives the metathesis reaction to completion, often giving excellent yields.
Clever. Using escaping gas to push the reaction, what are the big applications?
Two stand out immediately. First, ring-closing metathesis, RCM. If you have a molecule with two alkene groups, a diene, spaced appropriately, and you treat it with a metathesis catalyst, usually in dilute solution, to favor the intramolecular reaction.
It bites its own tail.
Exactly. It connects the two ends, forming a cyclic alkene and spitting out a small alkene like ethylene. RCM is incredibly powerful for making rings of various sizes, from common 5- and 6-membered rings up to very large macrocycles, which used to be extremely difficult to synthesize.
Wow, making rings easily. What's the second one?
Ring opening metathesis, ROM, and particularly ROMP, ring opening metathesis polymerization. In simple ROM, you can take a strained cyclic alkene, like Norborn, react it with ethylene and a catalyst, and open the ring to form a linear diene. In ROMP, you use the ring strain of a cyclic alkene to drive polymerization, creating long polymer chains.
Okay, closing rings, opening rings, making polymers. Sounds versatile. How does the catalyst actually do the reshuffling?
The mechanism involves the metal alkylidine catalyst reacting with the alkene's double bond in a 2+2 cycloaddition to form a 4-membered ring intermediate containing the metal, a manila cyclobutane.
A square with a metal corner.
Sort of, yeah. Then this ring breaks apart in a different way, releasing a new alkene and forming a new metal alkylidine. This new alkylidine can then react with another alkene molecule, and the cycle continues, constantly swapping the CR2 fragments around. And maybe the most impressive feature, alongside RCM, is the functional group tolerance. Grubbs catalysts in particular tolerate an astonishing range of functional groups: ketones, aldehydes, esters, amines, amides, ethers, even alcohols.
So you can do this double bond reshuffling on really complex molecules without messing up other parts.
Precisely. It's become a cornerstone of modern complex molecule synthesis for that reason.
Is there a cool real-world example?
Absolutely. Alkene metathesis is actually being used to improve the properties of biodiesel. Biodiesel is often made from fatty acid methyl esters. Metathesis can be used to, say, cross-metathesize these esters with short alkenes to shorten the chains, or even remove the ester group entirely via ethanolysis, reaction with ethylene, producing hydrocarbons with much better cold flow properties, meaning they don't solidify as easily in cold weather.
From Nobel Prize chemistry to better fuel performance? That's fantastic. Well, that was quite a journey, an incredible tour through the world of organometallic chemistry. We started with the foundational workhorses like Grignard's and Gilman reagents, moved to the elegant cyclopropionation with Simmons-Smith, and then plunged into the truly revolutionary Nobel-winning palladium cross-couplings, Still, Suzuki, Negishi, Heck, and finally the amazing double bond dance of alkene metathesis.
It really has changed everything.
It feels like these reactions have fundamentally altered how chemists approach building molecules. What used to take, like we said, years or decades can now be done so much faster, so much more efficiently, and with incredible control.
Absolutely. And it's crucial to remember these breakthroughs, many of them really quite recent, aren't just sitting in textbooks. They are the engine driving modern drug discovery, enabling the synthesis of potential new medicines faster than ever before. They're vital in material science for creating new polymers, plastics, OLEDs, advanced materials with specific properties. And as we saw with biodiesel, they're even playing a role in tackling challenges in sustainable energy.
It really makes you think.
It does. What's the next big transformation that organometallic chemistry will unlock? What seemingly impossible reactions today will become routine tomorrow? The potential feels almost limitless.
A perfect place to leave it. It's a field that constantly surprises and innovates. A huge thank you for guiding us through that complex landscape. And thank you, our listener, for joining us on this deep dive. We hope you feel a bit more clued in to the amazing power of organometallic chemistry. Thanks for being part of my deep dive family. We'll catch you on the next one.